In this video, we will talk about the connection between momentum and a physical quantity called impulse. First, we will introduce impulse as it relates to force. And then, by using Newton's second law, we will see how impulse is related to momentum. In particular, we will talk about the so-called Impulse-Momentum Theorem. And finally, we will solve some problems based on these concepts that we introduced. Impulse is a vector quantity. We usually represent impulse with the letter capital J. The SI unit for impulse is newtons seconds or kilogram meter per second. To understand the concept of impulse, let's look at this diagram here. So what you have is a bat and a ball approaching this bat. Let's see what happens at the moment the bat hits the ball. When the bat hits the ball, it will exert a certain amount of force on the ball. We shall call this force F0. Let's assume it is a constant, and this constant force acts for a time interval of delta t seconds. In other words, delta t is the contact time between the ball and the bat during the collision. If we were to plot this constant force on an ft graph, force time graph, it will look something like this. So since the force acts only during a finite time interval, let's call that delta t, that is this one. So the graph looks something like that. So delta t is that time interval right there, and that is the magnitude of that force, F0, which is a constant. So again, F is measured in the units of newtons and time is measured in the units of seconds. So the impulse exerted on the ball by the bat is written in a following manner. The impulse is given by the product of that average force and the time interval. So as you can see, since average force is measured in the unit of newtons and time interval is measured in the units of seconds, impulse would have an SI unit of newtons seconds. Another thing to note here is, since force is a vector, it follows that impulse must also be a vector because time is a scalar. One can also immediately see that the magnitude of the impulse is F0 delta t, and F0 delta t is quite simply the area under this graph, the shaded region in red right there. So a graphical interpretation for impulse is that impulse also equals to area under force time graph. We should add that the force that gives rise to impulse is a force of very short duration. So it's common to have delta t within the range of milliseconds. Now what if the force F during collision is not a constant, but it varies with time t, as shown by the following graph? So as you can see, in this case, the graph is not a rectangle as we presented before, but it has an irregular shape to it. Now let's say, as before, the force starts to act from t1 seconds to t2 seconds, and of course t2 minus t1 is delta t, the very small time interval. So how do we write impulse? Now since we know impulse is quite simply the area under this graph right here between t1 and t2, we know such an area can be represented by an integral. So it's an integral of that force function with respect to time, with the lower limit being t1 and upper limit being t2. So this is how we write down impulse for a generic force that is a function of time. This will bring us to the subject of how impulse and momentum are related. Now, since from Newton's second law, the net force equals the rate of change of momentum, we see that by integrating the above equation with respect to time, we get the left hand side is quite simply f dt, and the right hand side is dp dt dt, which is just dp. So if the force is acting between t1 and t2, causing the momentum to change from, let's say, p1 to p2, and recognizing the left-hand side is quite simply impulse, this will give you an equation: impulse equals the change in momentum. The change is p2 minus p1. So we have another definition for impulse. Quite simply, impulse equals the change in momentum. This is what we call the Impulse-Momentum Theorem. We also see, since the SI unit for momentum is kilogram meter per second, impulse can also be quantified in kilogram meter per second, as we discussed earlier. Now, let's look at a problem associated with Impulse-Momentum Theorem. So you have 0.5 kg ball, that's this one right there, thrown horizontally against a wall, that is the wall. It hits the wall with a speed of 20 meter per second. If the ball rebounds horizontally with a speed of 12 meter per second, calculate the impulse that acts on the ball during the contact with the wall, and assume the ball is in contact with the wall for 0.015 seconds, and if so, find the magnitude of the average force on the ball during the impact. So let's calculate the impulse. Impulse from Impulse-Momentum Theorem equals the change in linear momentum. The change in linear momentum is momentum final minus momentum initial. Now, momentum final is 0.5, that is the mass of the ball, times the final velocity, which is to the right. So that's going to be 12I hat. And the initial momentum is 0.5 times 20 meter per second, and 20 meter per second is going to the left, so that will be minus 20I hat. And when you do the sum, you will get 16 kg meter per second. So that is the answer for part A. Part B, you want to find the average force. Now note, the force can be found by simply taking the impulse over the time interval. Now, by the way, the impulse is in the direction of I hat. So since impulse is 16, we have calculated from part A, and the time interval is 0.015 seconds, so 0.015. So when you do the division, you will get the average force acting on the ball during the contact with the wall. And the force turns out to be 1067 newtons. And of course, the direction, if you're interested in the direction, then the direction of the force is also I hat, the same as the direction of the impulse. So that solves the problem. Problem 2. A ball with mass 0.35 kg is initially moving to the left at 20 meter per second. It's given by this diagram, so this is the initial state of the ball. It is then kicked with a speed of 28 meter per second, right there, in a direction of 42 degrees above the horizontal. So that is the final state of the ball, and the ball is actually moving to the right now. Now calculate the impulse and the average force during the kick, taking the contact time between the foot and the ball to be 0.02 seconds. So impulse, we can use the Impulse-Momentum Theorem to calculate that. It is the change in linear momentum. So the change in linear momentum is the momentum final minus the momentum initial. So the momentum final is, from that diagram right there, since the mass of the ball is 0.35 kg, the final velocity of the ball is 28. It has two components, the y component and the x component. So the x component is 28 cosine 42 degrees I hat, and the y component is 28 sine 42 degrees j hat. So 0.35 times that, the quantity in the bracket will give you the final momentum. Now the initial momentum is given by, again, 0.35 times the initial velocity. The initial velocity is minus 20I hat. So as you can see, this minus and this minus will make it a plus, giving you 14.28 I hat for the x component of the impulse and 6.56 j hat for the y component of the impulse. So this is the answer for impulse in the unit of Newton seconds. Having found the impulse, we can proceed to get the average force. So the average force is given by the impulse over the time interval. The impulse vector is 14.28 I hat plus 6.56 j hat. The time interval, the time of contact, is 0.02 seconds. And when you calculate, you get the following, which is 714 I hat plus 328 j hat newtons. And that solves the problem. The following problem tests the graphical interpretation for impulse. So you have a force-time graph, represents a collision of 100-gram object with a hard surface. Initial velocity is 32 meters per second to the left, perpendicular to the surface. After colliding, the object rebounds perpendicularly to the right with the same speed. Find F naught. First, let's calculate what the impulse is. That can be computed. We know that is quite simply the change in momentum, according to Impulse-Momentum Theorem. So the mass is 0.1 kilograms. The final velocity is 32 to the right, so it's 32 I hat. Initial velocity is 32 to the left, so it's minus 32 I hat. And that's going to give you 6.4 I hat Newton seconds. So that is the impulse involved. We can equate this impulse to area under the graph. Consists of area 1, 2, and 3. 2 triangles and 1 rectangle. So 6.4 I hat, or the magnitude 6.4, equals the first area, which is half times, this is 1 millisecond, so it's 1 times 10 to the power minus 3 times F naught. And area 2 is a rectangle, so again the interval is 1 times 10 to the power minus 3, it's milliseconds, times F naught. And the third area is another triangle. It's half times 1 times 10 to the power minus 3, which is this time interval, again times F naught. So that will give us 6.4 equals 2 times 10 to the power minus 3 F naught. And solving for F naught, we will get 3,200 newtons. And that solves the problem. Thank you for watching.